It's my honor to introduce our plenary speaker, Professor Reed Maxwell. He is the William and Edna McKellar Professor of Engineering and Applied Science in Civil and Environmental Engineering at Princeton and also at the High Meadows Environmental Institute. At Princeton, he also directs the Integrated Groundwater Modeling Center, and his research interests are focused on understanding connections within hydrologic cycle and how they relate to water quality and quantity under anthropogenic stresses. He has a long list of honors and awards, including fellowship from AGU, 2018 Bosnisk Lecture, 2020 Henry Darcy Lecturer, and a research award from Colorado School of Mines. And he is well known in hydrologic community for his groundwater modeling work, and that is what we'll be listening to, I guess, at the continental scale. So without further ado, it's my honor to welcome our plenary speaker. Thank you.
Great. Thank you all so much for inviting me to speak. I think there's going to be a lot of synergy between what I'm going to talk about and all the amazing talks so far today. So I'm just going to kind of kick things off and say water is becoming a thing. If you haven't noticed, I've been in the water game about 25 years, which is a long time. Nobody cared about water 25 years ago. You turned on the tap, it came out, everything was good. That's much different now. So if we look at, this is the NOAA extreme events. This is from 2022. They do this every year. A lot of the extreme events have already been things that have been talked about, right? So we just heard about flooding, we've heard about land cover change, we've heard a lot of really interesting things. Each of these icons is a weather and climate disaster that resulted in excess of $1 billion in damages. And if you look at the sum total from the past 5 years, we're talking $500 billion, more than $500 billion in damages. And these things range from droughts, fires, extreme weather, hurricanes, snow events, all over the map. So, I know a lot of you have laptops open. That's great. You guys are all well prepared. We're going to be interactive in this talk. So if you can go to pollev.com, read Maxwell 700 for those of you not on a phone. Otherwise, shoot the QR code, and it should take you to the poll. I know, everybody wants to go to sleep right before lunch, but I'm going to keep you awake. So the first question is, what is the largest surface water reservoir in the U.S.? Looks like we've got Great Lakes, common choice. We've got some Great Lakes named out. You guys are so close. We've got the dam, but not the lake. There we go. Lake Mead. So Lake Mead is, in fact, the largest surface water reservoir in the U.S. This is a picture from about 20 years ago, 2020, the last time it was full. Sorry, 2000, the last time it was full. This is summer of 2021, which is when it hit its recent low point. This is at about 33% capacity, which means that it's actually the lowest capacity since the Hoover Dam was constructed and Lake Mead was filled behind it 100 years ago. So, incredible water and climate disaster. And in fact, so large you can see it from space. So this is the same time period, 20 years ago. This is obviously NASA satellite imagery. Just to orient you, right? So there's the Hoover Dam, right? One of the largest engineering projects in the world is just a couple of pixels on this image. And here's, the enormity of Lake Mead. Now, if we look at what it's at now, it's 33% capacity, right? We're talking incredibly low reservoir levels. Now, the trick with all of this is you think, okay, it's a drought, there hasn't been rain, there hasn't been snowpack. That's actually not the case. So if we either look at the median, this is red as the median snowpack over the past 50 or so years, lots of variability in snowpack, but actually no big deficit. There was a dry year maybe 5, 10 years ago. There's been dry years in the past, but it's not actually lack of snow that is, or lack of precipitation that is causing this drought, or causing the low reservoir values. This is a great paper by Chris Milley, who was just retired from the USGS. He was at GFDL in Princeton for most of his career. And in this paper in Science in 2020, he and his co-author analyzed the precipitation over the past century. So this is when Colorado River Compact was drawn up. And if we look at the precipitation, tons of variability. Statistically, it is the same over the past century. However, if we look at the temperature, there is a decided about 1.9 degrees Celsius increase in temperature in the upper Colorado over the past century. And this is actually what we call a so-called hot drought. And what this means is that the entire century of April 1 snowpack and September 1 reservoir levels, the entire century of those correlations no longer work with their stationarity. So reservoirs are not just rivers, right? So 96% of Lake Mead's supply starts as a snowflake in the Rocky Mountain headwaters. And of course, warmer temperatures accelerate snowpack, but more importantly, accelerate evapotranspiration. Plants everywhere need more water, and so what happens is there's less water that ends up in the system. Now, next poll. What's the largest freshwater reservoir in the US? Great Lakes. I know, Great Lakes, you want them to be the answer. They're huge. The Great Lakes are 20% of the surface water in the world. So of the surface water in the world, the Great Lakes are 20%, which is a lot. No idea. All right, we've got it. It's small, it's floating around there. We've got aquifer, and we've got groundwater, and we've even got Ogallala. So in fact, groundwater is our largest freshwater reservoir, right? So if the Great Lakes are 20% of all the surface water in the world, all of the surface water in the world is only 1% compared to groundwater. Groundwater is 99% of our unfrozen fresh water, and the closest water to you, pretty much wherever you are, is directly below your feet. So half the world's drinking water, half the drinking water in the US rather, about 60% of the world's agriculture. We've had some nice talks about water and food. 60% of that is driven by groundwater. Groundwater is also being depleted at an alarming rate. It's hard to see, it's very hard to model, and it's not included in most water management models. And as we just see, by the polls, everybody thinks about surface water, nobody thinks about groundwater. So even during the historic drought, if we look at a system like California Central Valley, I guess I should be using the pointer since there's apologies for those of you that are watching online. I'll use the pointer so that you can see what I'm pointing to. In California Central Valley, agricultural revenues remained at record levels. And this is an analysis done by the Pacific Institute. And what we see, these are agricultural revenues, total revenue, from 2000 to 2014. Now, 2013 and 2014 were the worst drought years in California Central Valley to date. Now, California has had another drought that was worse, but to date, historically, the 2013, 2014, and part of 2015 were the worst drought years. Yet, agricultural profits were higher than they have ever been. Why was that? Well, models and remote sensing can be blended together to show that, in fact, it was a ton of groundwater pumping. And this is a combination of a model simulation over the San Joaquin Basin. This was work done by one of my former PhD students, Lauren Thatch, who's now at the U.S. Bureau of Reclamation. This was published in Groundwater a few years ago. And this is also compared to the GRACE satellite remote sensing product. Now, the GRACE satellite remote sensing product, 1 pixel of that product is the entire size of the San Joaquin watershed. So very coarse resolution. So it's very hard to disaggregate to ask these sort of system level or decision level questions. However, in some follow-on work that Lauren did, she ran a whole ensemble, so millions of CPU hours worth of simulations, each of which calculated a pumping and irrigation rate that matched the deficit seen in GRACE, so the total water deficit. And what we can do is we can actually back out how much groundwater pumping that was. And what we see is that during a non-drought year, there's something like, I don't know, maybe 8 cubic kilometers of water pumped out of the San Joaquin, of the Central Valley. But that jumps to about 28 cubic kilometers during the drought. Now, to give you a flow, cubic kilometers, about 810,000 acre feet. Most of you probably don't even know what an acre feet is. That's okay. Most people don't know what an acre feet is. So if we put this in context, the average flow in a good year of the Colorado is about 14.8 million acre feet, right? So farmers in the San Joaquin may have pumped 1.5 Colorado rivers out of the Central Valley during the drought to keep agriculture alive and well. Now, groundwater is a national issue. Groundwater pumping is a national issue. This is some work done by my friend and collaborator, Professor Laura Condon. Laura is in the Hydrology and Atmospheric Sciences department at the University of Arizona. And Laura was really interested in understanding broadly this impact of pumping, pre-industrial and current. And so she developed 2 different models. One that was pre-industrial, so no groundwater pumping, and then one that was sort of a current model that had our best estimate of groundwater depletions and groundwater pumping. And running these big simulations, she could look for things like how much have streams declined, how much stream decline has happened over the past century due to groundwater pumping. And this is what's shown here. And so we have streams that are unimpacted, here, unimpacted down in blue, all the way up to streams that have disappeared, and overlay with the major aquifers. Now, what we see is, there's areas where streams have disappeared. These are anecdotally pretty well tracked, and they track with areas that have been, where streams have disappeared in the real world, not in the model world. We also see areas where this propagates down the stream network. Another really important impacts of pumping from hundreds of miles away may impact stream flow downriver. The other thing that's really surprising is that if we look over the Colorado River Basin, one of the things that jumps out is there's actually a lot more pumping than you might think, and there's a lot more stream depletion than you might think. And so in addition to climate change, in addition to all the other stresses in a very tightly allocated basin, there is groundwater pumping, and we don't know how much it is, and it may be depleting streams. Now, it's not just the western US that is challenged by a changing climate. This is a great animation by Yale 360. This is based on a paper by Seeger et al. That was in Earth Interactions that shows the 100th meridian, which is commonly known as the aridity divide between the western arid US and the more humid eastern US, that it's moving east. And this animation shows that it's actually moved quite a few degrees east. And we often say that climate change is exporting the West water problem east. Now, in another paper that Laura led, this was published in Nature Communications in 2020 in collaboration with Adam Atchley, who's staff at Los Alamos National Laboratory. We ran a number of large-scale climate simulations over the entire continental US using this really extensive hydrologic model that includes groundwater. And we looked at the changes. We looked at a lot of different things, but one of the things we looked at is the changes in evapotranspiration across aridity for different basins. So we have, say, the Ohio, which is a more humid basin, compared to the upper Colorado, which is a much more arid basin. And we can plot this as a sensitivity. So this is ET change per degree, and then per degree of warming. And what we see is that our most arid basins in the US are tapped out. So as they warm, they're going to be less vulnerable, less sensitive to climate change. Our more humid basins actually are going to change quite a bit, and actual ET is going to increase quite a bit, and they're going to be more vulnerable still. We can also think of this in terms of how much depletion, how much groundwater depletion is caused by increases in temperature, increase in potential evaporation, increase in actual evapotranspiration. And it's actually a really staggering amount. If we look at, we did a 1.5 degree increase, which is the IPCC sort of target, which we probably won't hit, but that's the target, a 2 and a 4 degree increase. And what we see is something like 119,000 million cubic meters of water taken out of the system over the US under a 1.5 degree warming scenario. That's 4 Lake Powells, or, to put it in Great Lakes standards, a quarter of a Lake Erie, right? Equivalent to, probably about 10% of our, or 5% of our total surface water reservoirs. A 4 degree warming case is 10 Lake Powells, or 3/4 of a Lake Erie. Just these staggering amounts of water. Now, to kind of get to the second half of this talk, we face really hard problems, bigger droughts, changing nature of droughts, depleting groundwater. We have these tools that I've demonstrated that can really understand these complicated changes, but they're really, really expensive. The simulations I've shown you are probably about 15 to 20 million CPU hours mostly on Cheyenne, on the NSF in-car supercomputing system. And it's amazing that we can do that, but this does not place any of these sorts of tools in the hands of water managers. And there's a big gap between these tools and their accessibility. Now, as I mentioned, large-scale modeling has really become widespread. These are 2 papers. One, this is led by Tom Gleason. This was in GMD. This was led by Laura. This was in Water Resources Research. Big, community activity around developing these large-scale hydrologic models that include groundwater. And in my own group, we've been doing a lot with advancing, sort of the traditional computational national model development. And just to highlight, this is also a paper by Daniel Tiarina, who's in my group and PhD candidate in civil environmental engineering at Princeton. And this is Chen Yang, who's a postdoc in my group at Princeton. And they have been leading 2 big efforts, a big data effort, which is just in press now, in groundwater in early release, and all of these different data sets at high resolution that all go in to build these massive hydrogeologic, soil, and topographic data sets for use in our modeling systems. And then in addition to that, we've also simulated these. And this paper was led by Chen and is in press in Journal of Hydrology. And what you see is this unprecedented ability to capture water table depth over the US at incredibly high resolution for the entire continent. And these models also rigorously validated against almost more than 1 million observations. And they show a lot of promise in terms of performance. The problem is they're not accessible to users, right? We don't have a way to easily, even if a user wants to look at the results. And so what we've done is over the past few years, have developed these 2 main platforms that I'm going to talk about in the latter part of this talk. The first is the HydroFrame platform, so you can go to hydroframe.org, and I'm talking about a new tool that we've just released, which is what we call subset tools. And what subset tools allows you to do, and it's on a read the docs, it's all completely on GitHub, it's open science, open published, open source, to share our publicly available data. And what you can do is you can pick any watershed, pick any location, and grab any of these archived results, either from the so-called CONUS 1 results, which I showed earlier, or now the CONUS 2 results. And we've built an API for this, so it's in beta right now, but it's an open API that anybody can use these, access these data. And they're all housed on what we call the Princeton Hydro Data Center, which is a 3 petabyte data share that we have complete control over and can manage access. And so you can set up and run your own subset model, you can explore the data, you can do all sorts of different things. And it's been a huge amount of work in tandem with the model simulation and development. We also have, I'm not talking about it in this talk, but we also have a whole suite of education outreach tools, for example, the Parflow Sand Tank as well, which has been part of this project. Now, in addition to model simulations, we also bumped into a major challenge in terms of hydrologic data. And so originally we built APIs to go grab a whole suite of different hydrologic data from the original data sources. The APIs were clunky, they were non-standard, there were a lot of issues. So we ended up cloning 4 federal databases. So we have all of the US stream flow, groundwater levels, we have all the SMAP soil moisture, SNOTEL, USDA scan, we have Ameriflux, we have precipitation and temperature. All of this is continuously updated, so it's less than a week old from current. Everything is set up as a cron job. Everything is automatic QA/QC. So if there's data that's flagged as being provisional, we'll go back and check to see when it's actually no longer provisional. And there's a unified data catalog and a unified interface for all of these data. So you could just give a long box and say, I want any of these data, and it would return back any time frame, any of these different data. And this is also open software, open source on GitHub. Now, the last piece, a sort of theme of my talk, is that these integrated hydrologic models, we've made them more accessible, but we're still running them on supercomputers, and they still take a lot of computational time. They're very expensive to run. And so the last project I'm going to talk about is a project called Hydrogen. And Hydrogen is actually a National Science Foundation convergence accelerator. We're in the second generation of convergence accelerators. Laura Condon at Arizona is the PI. Peter Melchior, who's actually an astrophysicist at Princeton and machine learning expert, is one of the co-PIs. And I'm going to just highlight some work from our what we call the HML, or Hydro Machine Learning team. And this is a collaboration between University of Arizona, Princeton University, Cyverse, and the Bureau of Reclamation. And so, first off, another poll. One of these is an imposter. So one of these is a hydrologic model, and one of these is an AI. And so now I want you to pick which is the physical model, A or B. I mean, I can jump back and forth if you want to stare at it and zoom in, but it's sort of like an on-the-fly Turing test. It's always so suspenseful watching the I'm going to call this quorum pretty soon. Great audience participation, by the way. I appreciate all of you being engaged. So in fact, you are correct. B is the imposter, although statistically speaking, they're indistinguishable. So, and I've done this a few times now, and it's basically 50-50, A and B. However, congratulations. The Turing test failed, you spotted the imposter. And what we're doing in this project is we're constructing emulators of hydrologic models. And so these are designed to reproduce and be a surrogate of these national scale simulations that you just saw. Now, they're emulating all the model physics in 3 dimensions. So they emulate the entire 3D pressure field, they're given the same inputs as the underlying model, and they're all trained nationally. And we've got some early papers on this that sort of were the proof of concept, and I'm going to highlight some of the work here. This is work from Huang and Elena, two of the postdocs I showed earlier, and you can look up these publications if you're interested in more information. Now, one of the challenges, and I alluded to this earlier, but one of the challenges of data-driven approaches is that if there's no extreme events, if there's no warming in the data upon which you train an ML, it has no basis for knowing what that looks like. And in fact, what will happen is it'll do really weird things. Machine learning approaches are really good interpolators. They're actually not good extrapolators. And so Elena had the idea to basically provide additional criteria. So she manufactured droughts, she manufactured warming type scenarios, and included them in the training. Now, she could run them through the physically based model and then provide them as sort of additional data. And what ends up happening is it actually improves both the model's ability to predict extreme events, but also the model's ability just to predict normal events as well. So the more broad range that it sees, the better job it does. And in this case, this is all for soil moisture. Now, our application, as it's set up, is fully live, and we've had our first release. You can, there's a web page, and you can sign up for free access. And it does a number of different things, including running these machine learning emulators on demand. We also have the entire data catalog. We can do really interesting analysis with it. So for example, this is the hydro data. This is stream flow, groundwater, and snow. And you can turn on anomalies. So you can see an immediate snapshot or explore an immediate snapshot of what is the status of the US. And you can do a lot of really interesting types of analysis. And then in addition, you can click any watershed, and you will have a trained machine learning emulator model that'll run on demand. You can choose different scenarios. You can either choose an average or a warm, or from 40 years of archived forcing that we have also on the PHDC. Or you can do a true forecast, and it'll pull the CPC outlook, 3-month or 6-month outlook, and then it'll give you a statistical sampling of that CPC outlook as a forecast moving forward. And again, I'm showing soil moisture here, but it does water table depth, stream flow, snow. It does a full suite of simulations. And so, for example, this is Andrew Bennett. Andrew was a postdoc in the Hydrogen Project. Andrew is now new faculty at the University of Arizona. And this is the underlying emulator. And this is in review and James. And this is over the forecast periods. This is a 90-day simulation. This is par flow on the left. And this is the emulated simulation on the right. Now, again, indistinguishable, statistically the same performance, except the 90-day simulation doesn't need thousands of cores on a in-car supercomputer. It runs on a single GPU in 6 minutes. So we're talking several orders of magnitude speed up in terms of time. We're also doing straight data-driven approaches. This is work by Yuling Ma, who's a postdoc in my group at Princeton, also on the Hydrogen Project. This paper's also just come out in groundwater. And this is a purely data-driven water table depth estimate over the CONUS. And statistically speaking, this is the best estimate we have of how much groundwater we have. This is, a lot of promise. And the idea is that we can not only do the simulation emulators, but we can also combine these with data-driven approaches to provide even more robust answers to our water resources challenge. So water's finally getting the recognition it deserves. As was mentioned before, I think we're in a revolution of data and simulation capability. I think we really need to take advantage of that. And we have to bridge the divide between those of us who understand, curate, and create these data and those who want to collaborate to ask human-centered questions of it. So with that, thank you very much. This is a QR code for Hydrogenerations, which is the web page for hydrogen. And I'm happy to answer any questions. Thank you very much.